Hello. Today we're going to be talking about null spaces and column spaces. And this is another review video, so I expect you to know most of this stuff. But here's what I want you to know about this. So we're going to start out with a linear transformation T from the vector space V to the vector space U. And with that, we can choose bases for V and for U. These are going to be B and D, respectively. And we're going to choose these bases in order to write this transformation T as a matrix. So how that works is you apply the transformation to B1, the first basis vector here, and you see where that lands in the space U. Write whatever that vector is as a column vector in the basis D, and then that column goes here. It's the first column of our matrix. And then do the same thing for B2. That's the second column of the matrix, all the way up through Bn. Okay, so that's how we're going to be creating a matrix from a transformation. We can now talk about some generic properties of a transformation. So one of the standard things to talk about is the kernel. The kernel of a transformation is the set of elements of the domain, so of V, this is the same V as over there, the set of elements of the domain that gets sent to 0 in the codomain. Okay. So the next thing is the range, sometimes called the image, depending on who you ask. So the range of T is this set of U that actually get hit by some element of V. So in other words, it's the set of U in the codomain, in the target space, such that there is some element of the domain that hits it. Okay? And now I want to just point out that there is a natural correspondence between all of these things and some corresponding things after we choose bases. So before we choose a basis, we can still talk about V as a vector space, U as a vector space, T as a transformation. None of these things have anything to do with the bases. Same thing with these kernel and range. Okay? You don't need to have a basis in order to talk about what those things are. Okay? But after you choose a basis, all of these things become more concrete. We can actually talk about column vectors and matrices and actually have some nice grasp on some calculations that we can do with these. So, to start out with, V, after we choose this basis, B for V, is going to act exactly like Rn. Remember, the basis has n elements, and so by choosing this basis, we're saying V is essentially the same thing as Rn. Okay. After choosing a basis for U, which has m elements, we're saying U is the same thing as Rm. Okay, and as we saw right here, after choosing these two sets of bases, or these two bases, the matrix for T completely describes the transformation. So this T turns into the matrix A. So transformations in general get turned into matrices. Okay, and now the kernel we can also talk about in terms of the bases that we've chosen. The kernel is going to be something called the null space. So the null space has this notation, null of T, or we're specifically talking about a matrix, so I'm going to use null of A. So the null space is the set of vectors written as column vectors that when you write A applied to that column vector, up here, when you write A applied to that column vector, you get the 0 column vector in the target space. So it has literally the same definition, except instead of T of V, we write A times V, or A times X if you want. Okay. The range also has a corresponding notion after choosing a basis, and that is just called the column space, written as COL of A, col of A. Okay, so null space and column space are the same thing as kernel and range, just after we've chosen a basis, or bases. Alright, it's time to go over an example. So, we're going to start out with this transformation T, and this is going to go from P3 to P2. If you don't remember what those are, watch the previous video referring to those things. And our transformation is going to take this polynomial and send it to this polynomial. Okay, so this is a generic form of a polynomial. It covers any coefficients you want, and then this is a description of what to do with those coefficients to create a new polynomial in P2. Okay, so to start out with, depending on what the problem asks you in general, you might be asked to do a linearity check. This thing is linear. Here are some of the details, not all of them. So just to check additivity, if you add two of these polynomials together, then apply the transformation. The transformation is going to take the coefficient of, so we want this a right here. A is the coefficient of the x cubed, and we want to do 2 times that coefficient. So if we're adding these two polynomials together, the coefficient of the x cubed is a1 plus a2, and we want to do 2 times a1 plus a2. Okay, then we want to subtract off 5 times the coefficient of the x term, so the linear coefficient, and the linear coefficient for this sum here is c1 plus c2. Okay, so 2 times the cubic coefficient minus 5 times the linear coefficient, that's how many x squareds you have, and then similar for the rest of this. Okay, I'm skipping this step here, I'm skipping writing it down. All I'm doing in this step is distributing everything out and gathering all of the terms that have a 1 index corresponding to this first polynomial on the left, gathering all the terms that have a 2 index corresponding to the second polynomial on the right, and then noticing that it's literally going to be this stuff right here with some indices involved. Okay, and that is exactly what it means to be t of the first polynomial, and the second one's going to be t of the second polynomial. Okay, we also need to check that scalar multiplication works out well. So t of lambda times the polynomial is equal to lambda times t of the polynomial. That also works for this. This is a linear transformation. I'm skipping the rest of the details. Our goal now is to determine the kernel of t and the range of t. In order to write these down, we're going to want bases for each of these things. So determining the space's kernel of t and the space range of t is the same thing as determining bases for those two spaces. So in order to do that, we're going to start by choosing bases for P3 and P2, right, or domain and codomain. And then we're going to write a matrix using those bases. Okay, so I will point out that the basis here that we've chosen, 1x, x squared, x cubed, is ordered, and the order matters. Right? So for example, if I'm writing this ax cubed, I'm writing the x cubed term first, whereas it should be written last if we're thinking about this in that basis. So that will determine the order in which these numbers go in this matrix. Okay, so the first column of this matrix is going to be the image of this first vector in the basis for the domain. Okay, So we want to know, where does 1 get sent with this transformation t? And 1 is the polynomial ax cubed plus bx squared plus cx plus d, where a, b, and c are all 0 and d is 1. Okay, that's the same thing as the polynomial 1. And t sends that to this polynomial. Remember, a, b, and c are all 0 and d is 1. That's the same thing as saying 2 times 0 minus 5 times 0 x squareds plus 1 plus 0 x's plus 0. So in other words, we just have 1x. 1x, written in terms of the basis for the codomain, is 0 1's, 1x, and 0x squareds. So we can write that as 0, 1, 0. Okay, now we're going to do the same thing for the next basis vector, this x here. And x is the same thing as having c equal to 1 and a, b, and d all 0. Okay, so if c is equal to 1, we're going to get negative 5x squared, and then the rest of it is 0. So we have negative 5x squared. Written in terms of this basis, 1x x squared, I have negative 5 times the third basis element plus 0 times the other basis elements. Okay, so now we're going to do the same thing for x squared. So x squared is going to be where b is 1 and a, c, and d are all 0. So if b is 1, this is the only place that b appears. So we're just going to get 3x and then no x squareds and no constant term. So 3x. That's 0 1's, 3 x's, and 0 x squareds. All right, and finally for x cubed is where a is 1 and the rest are 0. So a appears here and here, and so we're going to get 2 times 1 x squareds, and then plus 1 in the constant position. So 1 is the constant, so I have 1, 1, I have 0 x's, and I have 2 x squareds. All right, this is the matrix for t with respect to these bases. Okay, so WRT is with respect to, if you're not familiar with that. All right, so I just want to point out that A is 3 by 4. It's a 3 by 4 matrix. And we could have determined that before we started this process by just saying this is a 3-dimensional space, this is a 4-dimensional space, so the matrix corresponding to it should be 3 by 4. All right, the next step in this process of calculating a basis for the column space, which is the one we're starting with. So we're calculating a basis for the column space by row reducing A. So in order to row reduce this, we don't have to do much. We just have to switch around the positions of some rows. So I'm going to write the second row first because it has a 1 in the first column. Okay, so 1, 0, 3, 0. That's our new first row. Okay, and now I'm going to write the third row. And finally, the previous first row. All right, this is not reduced row echelon form, but we don't actually care about that. So by reduced row echelon form, I mean we could make this negative 5 equal to a 1 by dividing the second row by negative 5. We could also zero out this 2 by doing this row minus 2 times the last row and replacing that in the second row's position. We don't need to do either of those things. We just need some echelon form. We don't need it to be reduced. So we're going to leave it like this. And what we're going to look for is pivot positions. So a pivot position is an entry in the matrix where all entries to the left of that are 0. Okay? So this 1 right here is a pivot position because all 3 of these numbers to the left of it are 0. Same thing with this -5. Okay. Oh, sorry, I should say it's a non-zero entry where all entries to the left of it are 0. So this 0 right here is not a pivot position. You have to be non-zero to be a pivot. Okay. And then this one is vacuously a pivot position because there's nothing to the left of it. All right, once we do that, the only thing we care about with these positions is what column they lie in. These columns are called pivot columns. So the first, second, and fourth columns are pivot columns. And what we do with that is we go back to the original matrix that we had and say the first, second, and fourth columns, the corresponding columns, are pivot columns for this matrix. So the pivot columns don't change when row reducing. And what that means is well, let's just say this. The goal is to find a basis for the column space. A spanning set for the column space is always going to be the columns of the matrix. That's what the column space is. That's what it means to be a column space. Okay? So the problem with just taking all 4 of those things is that it's not a basis because there's too many things, right? There's this column right here is an element of R3, and we would have 4 different columns. That's 4 vectors in R3. That's too many to be a basis. So in order to find a basis, we need to get rid of some. Remember, we have that theorem that says if we have a spanning set, so a set that spans the column space here, in order to find a basis, we could search for certain vectors in that spanning set, get rid of them, and we're left with a basis. This is the process for doing that. Finding the pivot columns tells you which ones you need to keep. So these red ones we need to keep, and this one is extra. In other words, this column can be written as a linear combination of the other columns. Okay. So we're ready to write down the column space. Okay, so this basis is going to be the 3 columns that I have circled. Okay, so 0, 1, 0, 0, 0, -5, and 1, 0, 2. Okay, this is almost what we want. Our goal is to find the range of this, or a basis for the range of this. Well, in this case, we have 3 vectors that are a basis for call A. When we translate them back into polynomials, remember this is 0 times 1 plus 1 times x plus 0 times x squared. These are all secretly polynomials in P2. When we translate that back, we're going to have 3 vectors which are linearly independent in P2, but P2 is a 3-dimensional space, so those 3 vectors must be spanning as well. Remember, they have the correct size and they're linearly independent, therefore they span, and therefore they are a basis. So a basis for the column space is the same thing as a basis for the entire space P2. Okay? But I'm going to use this particular basis that we found instead of the standard basis that we had for P2 up here. So the basis that we just found for the column space is this. This first one is x, so 0 times 1 plus 1 times x plus 0 times x squared. The second one is negative 5 times x squared. And the third one is 1 plus 2x squared. Alright, that's how you calculate range of T and the column space, and specifically bases for those. Alright, our goal now is to find a basis for the kernel of T, and to do that, we're going to find a basis for null A. Okay? And in order to find a basis for null A, we're going to take A and augment it. Remember that we're solving ax equals 0, right? The set of x vectors which satisfy this equation are exactly the null space. And when we're doing that, we are just solving a matrix equation. So we're going to do this in the standard way. So we're going to take our matrix, we're going to augment it with zeros, in other words, the zero vector. And now we're going to row reduce. Well, if you've already calculated the stuff for the column space, which we just did, you've already done some of the row reduction. And what that means is instead of using A here, you can just use the modified version that we had. So I'm going to get rid of A and instead skip a step by using our modified version, which was this echelon form augmented. Okay, so remember this is not reduced, but that doesn't really matter too much. We don't need it to be reduced for this process. So let's write down what we have here. So just recall, this is the number of x squareds we have. This is the number of x cubes we have in this column, number of x squareds, number of x's, and constants. Oh, sorry, I did the mistake that I warned about earlier. This is the number of constants because that's our first basis vector. This is C, this is B, and this is A. Okay, so this third line here we can read off as A must be 0. So the third line says that A must be 0. The second line says negative 5 times C, negative 5 times C, plus 2 times A must be 0. And the first line says 1 times D, just D, plus 3 times B must be 0. Okay? So these are the three equations we get out of augmenting this. And now we want to turn this into a basis for the null space. And I just want to point out before we do that, we actually already knew all of this stuff before starting. So all of this stuff is just saying that the first one says a is 0. The second one says 2a minus 5c is 0. And the third one says d plus 3b is 0. Well, we want to get to the 0 vector here, and therefore all coefficients of this polynomial that we're getting to must be 0 to be the 0 polynomial. So we can read off that stuff just from this right here. We don't have to go through this process. Okay. So if you do start out with a matrix, you do want to go through this process, but if you have a nicer format that isn't in matrix form, you don't have to switch to a matrix in order to calculate this stuff. Okay. So now we're going to use this to come up with a basis for the null space. Okay. So I'm going to think about this as we have some vector a, b, c, d, and I know some stuff about a, b, c, and d. In particular, a must be 0. So that top entry must be 0. Okay, well, if a is 0, then this term right here is 0. And I know that negative 5c must be 0. So that's going to tell me that c is 0 as well. Okay, so the first and third entry of this are 0. And this is the only interesting one we have. So d plus 3b equals 0. We're going to pick a free variable, and it doesn't matter which one we choose. I'm just going to solve for the easier one to solve for. So this is d is equal to negative 3b. So b is going to be my arbitrary choice, my free variable. And I'm going to leave that as a b. And whatever b that I put there, d must be negative 3 times it. Okay, we'll see another more interesting example of this next, but for now, I'm just going to factor out the b, and we have b times the vector 0, 1, 0, negative 3. Okay, so in other words, if a, b, c, d is in the null space, is in null A, that means that it is a multiple of this vector right here. It's b times that vector right there, but I don't really care that I'm calling it b. It's some number times that vector. So this right here, this vector, is a basis for the null space. So we would have gotten a linear combination here if we had a more complicated basis with more than one element. 0, 1, 0, negative 3. Is the basis for null A. Okay, once we have that, we can write this as something in terms of the kernel by just turning this vector into a polynomial. Okay, so I'm just going to write this vector as 0 times 1 plus 1 times x plus 0 times x squared minus 3 times x cubed. And this polynomial by itself is a basis for the kernel of T. Okay, so one more thing before we move on to the next example is we have this theorem called the rank nullity theorem, which says that the dimension of the column space plus the dimension of the null space is equal to the number of columns. So why is it called the rank nullity theorem? Well, this number right here, the dimension of the column space, is usually called the rank of the matrix. Okay, and the nullity comes from null space. Number of columns is the same thing as the dimension of the domain. Okay, so in particular for our example that we have, the dimension of the domain is 4. And 4 is equal to the dimension of the null space. So there's one element in this basis here, so the dimension is 1. And then if you recall, the dimension of the column space was 3. We had 3 elements in our basis. And 3 plus 1 is 4. This equation will always work out. So it's one quick thing you should always check when you're doing these calculations to make sure you didn't make some silly mistake. All right, we have a new problem here. Our problem is to find a basis for this set. Okay. So U is the set of polynomials in P3 such that evaluating at 2 and evaluating at -4 yield the same number. Okay. This is very similar to some of the sets we saw in the last video dealing with the definitions of these PKs. And this is linear for the same reason. Okay? So you should check that U is actually a vector space by checking that it's a subspace of P3. I'm not going to do that part. You can just trust me it is, or you can check it yourself. So how do we solve this? We're looking for a basis, and it turns out a convenient way to do this is to define a map T from P3 into R. Okay, the map that I'm going to define looks like this. I'm going to take a polynomial P of x, I'm going to say, let's send this to the real number, which is P of 2 minus P of -4. Okay, so why do we do this? Well, let's take a look at this number we have right here and this equation defining the vector space U. Okay, saying that P of 2 is equal to P of 4 is the same thing as saying P of 2 minus P of -4 is equal to 0. And saying that the transformation applied to something is equal to 0 is the same thing as talking about polynomials in the kernel of T. So the kernel of T is the set of polynomials in P3 such that T of them which is this, is equal to 0, or the 0 element of R, which I'm going to not write a vector symbol over because it is literally an element of R. Okay? So this equation right here is the same thing as this equation, which means that this is equal to U. Okay? So finding a basis for U is the same thing as finding a basis for the kernel of T. In order to do that, we're going to go through our same process, except we're going to have some more interesting things to deal with. Okay, so to start out with, we're going to choose a basis. So we need to choose a basis for the domain and the codomain. I'm going to again pick the standard bases. So 1x, x squared, and x cubed. For P3. And I need a basis for the vector space R. I'm going to call that R1 actually. And why not? Let's just put that over there. Okay. So the basis for that is just going to be the element 1. Okay, so we have bases, and now we can write our transformation as a matrix with respect to these bases. Okay, so remember, A is going to be 1 by 4 because these are the dimensions of these spaces. Okay, so I have a 1 by 4 matrix. It's going to be 1 row and 4 columns. Okay, so the first entry is going to be the image of this first basis vector. So we're going to figure out where t sends 1. So if I have the polynomial 1 that I'm putting into t, so p is the polynomial 1, then p evaluated at 2 is 1 evaluated at 2, which is 1, and p evaluated at negative 4 is 1 evaluated at negative 4, which is 1, so 1 minus 1 is 0. So t of 1 is just 0. Alright, so that was the first basis vector. Gave us 0. That means the first entry in the matrix is 0. So now the second basis vector, x, I have the polynomial x that I'm plugging in here. X evaluated at 2 is just 2. And x evaluated at negative 4 is negative 4. Okay, we can subtract these two and get 6. So the second basis vector gets sent to 6. Alright, let's do the same thing for the third basis vector. T of x squared. This is x squared evaluated at 2, which is 2 squared. And then x squared evaluated at negative 4 is negative 4 squared. Subtracting these two things. So this is 4 minus 16. That's negative 12. Okay, and finally, I'm going to evaluate x cubed. So t of x cubed is 2 cubed minus negative 4 cubed. And this is 8 minus negative 64. So 8 plus 64 is 72. Alright, so we have our matrix. The next step in calculating the null space is to augment the matrix. This is something you don't have to write down, but you should at least think about what it means to augment this matrix and then write down equations based off of that. I'm going to just write it down. The equations that we get out of this are going to tell us some relationships between the coefficients of our polynomials in P3. So to start out with, I'm going to write down the format for our polynomials. I'm just going to say we have a times 1 plus b times x plus c times x squared plus d times x cubed. Okay. So a, b, c, and d are my coefficients in this basis that I've chosen. Notice that I'm writing in the opposite order that I wrote it in earlier. And now this right here, this 0 is the number of a's that we have. This 6 is the number of b's that we have. This negative 12 is the number of c's, and the 72 is the number of d's. Okay, so this one line of the matrix is an equation that we can read off that says 0 times A plus 6 times B minus 12 times C plus 72 times D is equal to 0. Okay, so we can get rid of some stuff here. So we don't need to write A times 0, and we can divide everything by 6. So we know that B minus 2C plus 12D must be 0. Okay, now we're going to choose one of these things to solve for. I'm going to solve for the easiest one, which is B, and say that B is equal to 2C minus 12D. All right, this is the only relation we have because we only have one row. And so we just have this one restriction. And when we try to write a generic vector here, A, B, C, D, we can replace the B with what it's equal to, 2C minus 12D. Okay, so our generic vector sitting in the kernel, sitting in the null space of this matrix, must look like this. Okay, so A, C, and D can be anything, but B must be equal to 2C minus 12D. All right, so we now want to rewrite this as the sum of, we want to rewrite this so it looks like a linear combination of some normal looking vectors that don't have A, B, C, and D in them. Okay. So I'm going to say this is equal to A times something plus B times something. I'm going to skip over that because there's no B's in here. Plus C times something plus D times something. All right, so this first thing says, the first one has to be A times 1. So there has to be a 1 there. And there's no other A's showing up, so none of the rest of these are contributing to the number of A's. Okay. There's no C in the first entry, so that's 0 C's. There's 2 C's in the second entry. There's 1 C in the third entry. And no D's. Okay, and finally, no D's up here, negative 12 D's here, 0, and 1 D in the last entry. All right, so hopefully it's clear that this linear combination is actually equal to this. And now we have our basis. So these 3 vectors here form a basis for the null space. So 1, 0, 0, 0. 0, 2, 1, 0, and 0, negative 12, 0, 1. Is a basis for null A. All right, now that we have our basis for null A, we can turn this into a basis for the kernel of T by just translating these vectors back into polynomials. Okay, so this first vector is just 1 times 1 plus 0 times x plus 0 times x squared plus 0 times x cubed. And that's just 1. So it's the polynomial 1. The second vector is 0 times 1 plus 2 times x plus 1 times x squared plus 0 times x cubed. So that is 2x plus x squared. And the third vector is negative 12x squared plus negative 12x plus x cubed. Okay, so this is now a basis for the kernel of t, which is the same thing as u. And we've now answered the question. I would like to also point out that we have 3 elements of our basis here, and we should know before we get to the actual calculation of the basis that there should be 3 elements of the basis. And the point at which we can realize that is up here. So we already know that u is equal to the kernel of this transformation, and we know that this transformation is onto R1 because we have a non-zero element of R1 that we hit, that's in our image, it's in our range. Okay, so we know that because we hit a non-zero thing, our range is the entire space. Okay, so our range is the entirety of R1. Therefore, the dimension of the column space, the rank, is 1. Okay, and by the rank nullity theorem, the rank, which is 1, plus the number of basis elements we're going to get in our answer, should be equal to the dimension of P3, which is 4. So 1 plus something is equal to 4. That something has to be 3. So we should know that there are 3 elements in here before we actually get to calculating what they are. Alright, thank you for watching.